So these are the lecture sessions, Monday and Wednesday. Then there are two lab sessions, and you're scheduled for one of those two lab sessions. But the work that I assign here, you can actually do all of it at home, so you don't have to come to the lab. But the lab is a useful place to go, especially in the beginning when you're getting started. So it turns out that there's usually free lab seats. Maybe not in the first week, but in the second and third weeks. So it means you can change the day that you attend lab. And if lab is very valuable to you, you can come both days. Because as I said, most of the time, there are free seats. So there is a book, but over the years, this is a book. Over the years, I've been formatting the class to be independent of the book because a lot of the books that cover the topic are very similar. And people coming into the class may have already purchased an expensive book on C++ programming for an introductory computer science class. And rather than spend the money and buy yet another textbook, you can use the book that you already have. If you don't have a book, then get this one. And if you want to save money, get the first edition instead of the second edition. Is there a question here? So I cover the topics. This book here, the sequence of topics that it covers is, I follow the same sequence. So I do essentially follow this book, but I don't have any other dependency on it. Is there a question? So we're studying a language called C++, and that'll be one of the learning goals, to learn how to write programs in C++. Although it's a tough language. So you won't learn all of the aspects of the language in 1 quarter. So if you go on and take the course that follows this, which is Computer Science, CSC 202, then you get more of the language. But chances are most of you won't use C++ after this class. Those are the chances are. Unless you're a computer science major, then you'll use it in school for sure. And when you graduate, what are the chances you use C++? Well, if you're a computer science or engineering major, then the chances are, higher than a normal person, obviously, but there are so many different languages, so many different development environments that the chances that you work in one particular language is small. But the thing is that learning one language is really learning them all. All of them have very similar structures. They all have things called conditionals, if statements. If it's raining, bring an umbrella. So that's called a conditional. So you want to take an action that's dependent on some condition. If the condition is true, take the action. If the condition is false, don't take the action. Every language has that. So we're studying that. And looping, like repetition, repeating activities until some condition changes. Every language has that. It has to have that. You need it to implement algorithms. You need it to solve information processing problems. So the second goal that I write here is that you improve your computational thinking skills. And so the specifics of the language, which may be important to you later on, is a bonus, but something that's very important, probably to most of you, maybe all of you, is computational thinking skills. How do you devise procedures that process data? That's essentially what we come up with here. All right, so I'm going to skip over this a little bit. these things in here, well, may not be meaningful to you now at this point, but they will be later on. But maybe the last two items, I want to talk about that. So in addition to learning about this language, C++, and the general concept of problem solving, algorithmic problem solving, well, that's not exactly the right term, solving information processing problems by developing procedures. So we think about how do we write a procedure to carry out some kind of analysis or processing of data. So we're learning that. In addition to that, we're learning two specific tools. One is called version control. So when software developers build complicated software systems, they almost always work together in a team. And so you're working on a single thing. You're building a single system. It may have lots of parts to it, but it has to be all glued together and run as a whole. Well, not always, but because you have client-server programming. So you do have modularization and so on. But the whole thing functions together as a whole. It needs to be tested as a functioning whole. And so you've got people working together, and so they're modifying the same thing. It's like a team of people building a house. You don't have one person building the house. You got people working together. And someone's installing the plumbing, another person's installing the electrical system, and you've got the roofers on there. They're all doing jobs, and they all have to sort of work together. You can't put the roof on until the frame is up, right? So you got to wait on the framers. So it's the same thing with software development. It feels a lot, well, although I never built a house, I imagine it's like building a house. You have to plan it out, work with different people that have different skill sets, and you build something that takes a long time and is complex. But some systems are very complex, like Windows. I heard that Windows has got 10 million lines of code. That's huge. Imagine reading a program with 10 million lines of it. No one reads the whole program, right? How can you read 10 million lines of computer code? So you've got a lot of people working on it, and you have to figure out how to break it into pieces. And you're working on one thing, so that you've got to sort of merge edits to this one thing. And this thing is basically in software development, they're files. So your basic unit is a file. You've got a file of information, like a word processing file, spreadsheet file, so on, an image file. You've got files, and the most important file is source code file. It's a file that contains machine instructions in some computer language that you write. And then you have other files that are part of the build, like image files, like when the GUI, the graphical user interfaces, rendered to the user. You see visual output, images and borders and things like that. So you've got image files, you've got sound files. When you click on a link or a button and you hear a dinking sound, well, there's a sound file in there that had to get loaded into memory, and so on. So you've got lots of different kinds of data. But the type of file that we're focused on in this quarter is called a source code file. So it's a file that contains what's called character data. All right, I'm going to try not to get too much off on a tangent there. And then, so version control. So we're going to learn a version control system called Git. And we're not going to learn it extensively. It's actually pretty tough to use in general. But in this context, in this class, we're going to keep it very simple. So it'll be pretty straightforward to use. So we use this version control system called Git and to submit your work. So you're going to sit down at a computer in the lab or at home or on your laptop in the library, wherever. And you'll be developing these source code files. And then when you're done, you'll write them into what's called a repository, source code repository. And then myself and the teaching assistant for the class, Darren Willis, will check out your work. So it's like we're working on a small software team of 3 people. So each of you will have your own remote repository that you merge your files into from your local development environment. So you'll hear me use the word remote and local a lot. So, you know, it's a networked world now. And so when you're working on a computer and you're referring to a computer, a lot of times you need to attach that adjective, remote or local. So local is the computer you're on, and remote is some other computer that you're working on through the network. And there's a Linux command line interface. Actually, I want to change that. I want to call that the Unix command line interface. Well, no, let me call it Linux. In our labs, we have computers that have the Linux operating system installed. So that's the interface that you need to learn, the command line interface. So you can see here, this is a command line interface. I type in commands. So I type in text commands, tell it to do things. And, you know, originally computers had really minimal interfaces. I mean, like, you know, flashing, blinking lights, and then they had these typewriters connected to them. And you would punch these cards and feed them into a card reader. That was your input. And then the program would run in this electronic computer. And then the output would be this physical typewriter would type out characters, you know, on paper, real paper. And so you would punch these cards, feed them through the card reader, you know, make the computer do something, and the output was this typed output. It wasn't like a printer now. We have these inkjet printers, you know, or all these different kinds of printers where you've got the print head, which can pretty much has very fine control over what it's getting printed. But in the old days, it was just, you know, an R, you know, was like a typewriter. I don't know if you've ever seen a typewriter. But it would, you know, strike a ribbon of ink and press the character R, you know, against the paper, and you would see an R. And that's how the computer used to output information. And then at some point they got rid of this card reader, because then you could just sit at the typewriter directly and enter in the information, and it would go into a file directly. And then you would have a monitor, a screen, but everything was character-based. All you would see are words. And you know, you would type a word into the computer, and it would type something back at you, and that was it. So that's called the terminal interface. And it turns out that the terminal interface is very, very handy. And you know, system administrators, computer programmers, and other sort of advanced users will use the terminal interface on any operating system. You know, Android, iOS, I think iOS. I've never used a terminal interface on an iOS device, but I'm guessing there's one. And Windows, they all have these terminal interfaces where you type in commands, which are strings of characters, and it's an instruction to the computer to do something. So that's something that you'll be using in this quarter, is the command line interface to the operating system. And so specifically, you know, there are different operating systems. So we're going to look at the Linux operating system. But actually, the command line interface for Linux is is practically identical to the command line interface for OS 10. So as you see, I'm using OS 10 here. So I can use the command line interface of OS 10. It looks just like the interface on the lab computers, but it's going to look different on a Windows computer. So the Windows command line interface is significantly different from the Unix style command line interface. So OS 10 and Linux are Unix systems, and Windows is different. So for instance, if I do ls, it means list the contents of a directory, and it's empty right now. But on Windows, ls would not work. But on Windows, it would be dir, which is to list the contents of a directory or a folder. Folder and directory, they mean the same thing. Okay, the word folder, the mean directory are interchangeable. So it says here, command not found. So if you type ls in a Windows command line interface, it'll say command not found. You might actually find it. This, what is it, Windows 8? That's where we're at, right? Windows 8. Does ls work on Windows 8? Might. So, and you can install programs that emulate a Unix command line interface if that's your style. That's what you want to do. But, so you need to become familiar with this this interface. Now, if you have a Windows machine and you want to work on the labs in the way that you see I demonstrate them, the way the students are doing the labs in the lab, then you have a number of different options. One option is you just make a connection. You get a remote terminal window to a lab machine. You just pick the lab machine in the lab that we use. Just log into it, and that'll work there. Let me show you how that works. Use a program called SSH on OS 10 and Linux. And on Windows, you'd have to use something else. There's a free program called Putty, P-U-T-T-Y, that a lot of people use. So you can use Putty to connect to a remote machine. Yeah, question?
So if I do most of my C++ programming on Visual Basic, should I?
Oh, you mean Visual Studio?
Yeah, Visual Studio. What's it?
You can use Visual Studio. That's good.
All right. Okay.
No problem. Yeah, if you're using Visual Studio, it's all right. If you're using Xcode, it's okay. Those are called integrated development environments. And they give you a GUI interface, a visual interface that you can use to carry out programming tasks. But I'm going to be illustrating the command line interface. And you have a Mac. Do you boot Windows?
Yeah, I have VMware, so I can run both at the same time.
What about Xcode? You can use that, right?
Probably.
You got to learn them both. So you got to do them both. Just a matter of time. Yeah, so Xcode is very important when you're building things for iOS and OS 10. And of course, the Visual Studio is the main tool that you use for Windows development. If you're using a language that's supported by Visual Studio. And there's alternatives too. I'll show you. What you do is you connect to this computer. The name. Computers have names. They have they have addresses. They have names and addresses. This is called the host name. And then it has an address on the internet. So I'm going to type in the complete address here. That's the whole address. So this is like, the country, the state, the city, and the street address, like that. So this is an internet domain name, we call it. No, oh, I don't have a network connection. I cannot illustrate this. Let me see if I can get one now. I forgot. Let me try.
It's been down for like the last last few hours.
What's that?
It's been down for the last few hours.
Oh, it's been down. Okay, so I'm not the only one.
Yeah.
All right, thank you. Okay, I'm not going crazy. All right. So I'm not surprised. But I came prepared. As long as the projector could break, then I'd be in trouble. So I can illustrate that later. Here's the readability. You know, when you write software, when you write programs, you have to think about making them readable by humans. I mean, obviously they have to be readable by the computer, or they won't work. So they have to be readable by two different things, by the computer and by humans. And readability to a computer is easier to achieve than readability to humans. Well, to readability to humans and computers is harder to achieve than just readability to computers. And so you'll see that when you take a writing class and you're learning the rules of composition, like how to write a clear sentence, how to follow punctuation rules, what's an adjective and how to use it and how is it used improperly and all that. And the reason for those rules is that hopefully if you follow the rules, that people can understand what you write. And it's the same thing with source code, that if you are clean and neat and choose good names and organize what you write so that you and others can read them, then it's easier to solve problems. So in this class, you need to think about and apply this list here of readability criteria. I don't want to go through this one after one, each item right now, but I'll come back and talk about these as we go through the class. But you'll need to become sort of aware of these principles and apply them to the source code that you write and submit. And myself and Jaron Willis, the teaching assistant, will apply these rules when we evaluate your submitted work. Here's the grading. It's just the standard, scoring, other information. Well, the Computer Science Club is an excellent resource. You want to be connected to the other computer science and engineering majors in the university here, or you don't have to be a major either, just anybody. But it's very useful. And every quarter they usually provide tutorials for beginners in this class to help them learn the command line interface and a basic C++ programming. So they'll be probably offering a workshop soon. So I'll try to remember to announce that to the class directly when that happens. Contact information. Here's the TA. It's me. And finally, here's the schedule. And this is Lab 1, Lab 2, Assignment 1, and then Quiz 1. So there's first things that we're going to do in the class. And the labs, like I said, you can do those in the lab, but you can also do those at home. So you've got a lot of flexibility there. And all of the problems, everything is provided to you in these web pages. So here is Lab 1. And so with these labs, I'm going to try to walk you through the labs, and this is a very hands-on course, by the way. And you'll be basically solving a sequence of problems. And then these labs kind of get you going there, and I show you the solution, actually. You carry it out. And but the assignment is similar to a lab. I'm going to give you problems to solve, which are similar to the lab problems, but I won't give you the solution in advance. And you have to figure those out on your own and submit those by some deadline. And that the day after the deadline, I will present the solution to those problems. You can see all the problems. They're already there now. So this is it. And look, the assignment, I made it look just like a quiz. So this is like, actually, the assignment is like a practice quiz, essentially. So I made it look like a quiz. And then after I review the solutions to the assignment, then in the next session, you'll take the quiz. Here's quiz 1. And just to help you out, I added some questions from previous quizzes. You can take a look at those. So here's an example of a quiz question right here. All right, here it is, number 1. Let's do this one. We'll just read through it right now. When the code in figure 1 runs, what does it output to the console? So you have code. So what we're looking at there is source code. These are instructions to the computer to do something. And one of the things that it tells the computer to do is to display something in the console window. This is the console window here. This is a console interface. This here, see the browser window? This is a graphical user interface called a GUI, graphical user interface. So we will not be writing programs that manipulate, that communicate with the user through a graphical user interface. We will not be writing those kind of programs. We will be writing programs which we launch from the console window and to which we display information inside of. We will display information inside of the console window. And so this line right here, and this part of the line, it's part of the line, that's actually a command that tells the computer to display a number in the console window. So it's a different language, right? It's not English, not French. It's C++. It's a computer language. And if you look at that C out, well, this is particular to C++. But if you saw this, if a programmer saw this line right there, just that, they wouldn't know what language that was. It could be JavaScript, it could be Java, it could be C++, it could be any large number of languages use that syntax, have this concept of a while loop, and they all work the same way. So this is an example, this code that we're looking at right here, this thing that I have highlighted is an example of something that's very generic. Not every language uses this syntax, but the dominant ones do. But this value here and this operator is only in C++. But this part of the expression, of course, that's everywhere. Not absolutely everywhere. Some languages that wouldn't use that syntax, they would use a different format. This one here, for instance, that's almost everywhere. That line of code would be interpreted the same way in almost every programming environment. I mean, there's some environments where it wouldn't be, like Lisp. It's a list-oriented programming language. So when execution passes through these instructions, so it's sequential, essentially, with some exceptions. So when you look at this, you know, there's two ways to look at something. There's the holistic way. You see everything all as one single thing. And then there's the analytical way, or the sequential way to look at something. So what students generally need to practice doing in this class and similar classes is to shift into sequential thinking mode. So when you see this, it's like you see a painting of a tree. You know, you see the whole thing. You know it's a tree. You don't go, well, this is a twig, and I'm going to look over here, there's another twig, and these two twigs merge together and form a little, I don't know what they call it, minor branches. And so that's essentially what you do when you look at this code. You need to look at the twigs. You need to see how they're connected together and form branches. And you need to see the leaves separately. You got to dig into the leaf and understand that there's cells there. You got to look at the detail. So that's, and then you stand back and you look at the whole thing, and the whole thing is a tree. So when you look at this right now, you just see this as a whole thing, as a holistic thinking. But how are we going to understand this? We're going to have to shift sort of our thinking and get into sequential mode. And you start, let's simulate how the computer would carry out these instructions. And we'll pretend we're computers running this program. These are instructions to do things, but we're going to do the thing that's on the top. So we're going to do the first thing first, the top thing first. See that little semicolon right there? That's an end of statement delimiter. So that means when the computer sees that, and when you see that, simulate in the computer, you say, well, that's the end of a statement. So I'm going to look at everything before that and understand what to do something. And this tells the computer, let's just tell you right now, this says computer. It's like in Star Trek, when you give commands to the computer. I'm an old guy now. You guys probably don't know Star Trek, right? But you speak to the computer and you tell it to do things. And here you're saying, computer, allocate memory to store an integer. Let it be known as I, and assign the initial value of 1 to it. Because that's how you read that statement. You're telling the computer to do something. Allocate memory. Not allocate memory in the disk drive, because there's all different kinds of memory. There's cache memory, there's disk drive memory, there's buffer memory on devices, and there's RAM memory. This tells the computer, allocate memory in RAM to store an integer. Well, it's 4 bytes, although there can be exceptions, but there's 4 bytes. Allocate 4 bytes of memory in RAM. Put the value 6 in there. And I will, later on, I'm going to refer to that chunk of memory, those 4 bytes, I will refer to that by the letter I. That's what that name is. So that's called an identifier. So it's a lot of programming has to do with naming things. You'll come up with names for things. Well, some things you don't name. And other things are names that you just conjure up yourself. So here, this I is something that's conjured by the programmer. But this name, INT, that's a given name. That's a name that's built into the language. It's short for integer. So I want information that's an integer. I want to represent an integer in computer memory. I need to use a name that's pre-existing, INT. And I say, this I should name an INT. And the INT that it names, let it be initialized to 6. Now, that's the end of that statement. Now, once this statement is done, we have to do the next statement. But if I ask you, just mentally right now, see, I've highlighted this statement, okay? I want you to mentally highlight the next statement. Character, each character specifically. So I didn't skip anything. I'm not sloppy here. I didn't say this, right? Or this. This is the whole statement, although I could omit the semicolon. So that's the whole statement. Mentally, that's the first statement. What is the second statement? Highlight in your mind the second statement. Tell me when you're ready. Ready? This is the second statement. Did you get it? There's only two statements. There's two statements at this level. So you have levels. The second statement is called a compound statement. It's a statement that has substatements in it. What this is, we do the first statement. We did that, created an integer 6. Integer I, initialized it to 6, and then we did the second statement, which was we iterated a number of substatements until a condition became false. So this is a compound statement. And look, we use these braces here to demarcate the substatements that are dependent, the substatements that this outer statement is controlling. So there's two substatements. This is one statement. See, statements end with semicolon, although this while loop here, there's no semicolon here, although you could put one in there, but it's optional. I didn't put a semicolon there. The semicolon terminates a statement. So these are two substatements. And I see that I'm off by one space, so I fail my own criteria here. See, this is a failure on my part. See, I'm using two spaces here to indent this, the first of the substatements. And then the second substatement is indented by 3 spaces. So that's -1 point for the instructor. Right off the bat, you're winning. Okay. So I want you to avoid that. When you write code, I want to see everything lined up when they're supposed to be lined up. So when you have substatements, you indicate the fact that statements are substatements are dependent on some outer statement. You indicate that by indenting them relative to the enclosing statement.
What about brackets? What about brackets? Do we have to line those up too?
Brackets. So you use brackets in different situations.
Because I don't mind mine up. I usually indent them.
Yeah.
Depending on which conditional.
Yeah.
Is that all right?
I'll have to take a look.
All right.
Yeah. So we've got two substatements. So here's the outer statement. So you see, we're breaking it down, a little piece by piece. So you're going to have to practice that. You got to dig in. You got to turn the radio off and get into a quiet space and start learning how to read a new language. And then also to write a new language. You're going to be writing these. You have to come up with solutions to these problems that I'm going to throw at you. So let's take a look at this. I'm going to keep, just to finish this off, let's see if we can read this. We read the first statement. Now let's read the second statement. The second statement is it's saying repeat something. And you can almost read it in English. While I is less than 66. So I is less than 66 is a condition. While that condition is true, while this condition is true, execute these two statements. So that means do the two statements, check the condition. Do the two statements, check the condition. Do the two statements. So you do that. That's a loop. So obviously the loop will be infinite. You'll never break out of it unless the substatements modify something that the loop condition depends on. So the loop condition depends on I. We can't modify 66. That's a hard-coded number. We're not modifying that number. It's not a name, it's just the number 66. But I is a name for an integer that we initialize to 6 in the first statement. We can modify the number which is stored in the memory named I. So the loop modifies it here. You see, I it says equals here, right? But you want to be careful. Don't think equals. Because actually, it'll be better to show, this is an operator. It's called the assignment operator. Take what's on the right-hand side and assign it to the left-hand side. Take the value that's on the right-hand side, some value, is an integer in this case. Take the integer that the right-hand side of the statement evaluates to, the right-hand side of the operator. Take the value represented by this expression. It's the word. I'm using a new word now. It's called expression. Statements are made up of expressions. It's like sentences are made up of, sentence fragments? Like, what do they call it? A predicate and what's the other thing? What's the opposite of a predicate? Subject, right? Subject and a predicate. So when you look at an English language sentence, and you break it down into sub-pieces, you say, oh, this is the predicate. This is the verb part of the sentence, and this is the subject. This is the subject part. So you can analyze these, the grammar of sentences in a language. It's not surprising that, grammar studies, linguists, and linguistics actually has a lot of overlap with computer science. And some very similar, there's some famous linguists that made significant contributions to computer science because there's so much overlap there. Anyway, this is an expression. The expression that's on the right-hand side of the assignment operator. It looks like an equal sign, but it's not. I mean, it is. It's a character equal sign. But it doesn't express the same thing that equals expresses, say, in mathematics. In mathematics, it says that the thing on the left is the same value as the thing on the right. But here, we're not saying that. We're not saying the thing on the left is the same as the thing on the right. We're saying, make it the same. Make it the same by changing the thing on the left. So it's called assignment. Assign what's on the right expression, the value that's determined on the right-hand side, and assign it to the thing that's on the left-hand side. So that's assignment. And that's how the loop condition will eventually become false. And when the loop condition is false, we stop repeating the substatements. And then we're done. This program only has 2 lines. It only has 2 statements. So once we've completed the second statement, we're done. I mean, it's a snippet of code, though. It's, maybe there's a larger bunch of instructions around this, but this is just the part of it that you need to analyze. Any questions on this? Well, we should look at the answer, right? What does it output to the column? So when I go show answer, what do you think it's going to have there? What's it going to show?
0 and 30.
What's it going to say?
0 and 30.
Anybody else?
30.
Well, here it is. It's going to print something here, right? It's going to print something here. And, well, this is a little hard to understand. Let's try to understand this. It has 2 operators. This is called an output operator. And this is also an output operator, but we have 2 of them in there. So we can this we can understand. Take the value stored at I and multiply it by 6. So if I were to say 1, then 6 times 1 gives 6, and that means assign 6 into I. So I was originally 1, but when the statement finishes executing, I now becomes 6. So I is used in the right-hand side to modify itself, essentially. So we can understand that statement, but what about this? Oh, and look, wait, before we go back to that, look, this statement, how many operations did we perform? 2. One was multiplication, the other one is assignment. Good, thank you for that. 2 operations. How many operations are performed in that statement?
2.
There's 2 output operations. There's a subtraction operation as well. Oh yeah, there are 2 operators, 2 different kinds of operators. There's a subtraction operator and there's an output operator. The thing is, we use the output operator twice. So we're executing the output operator twice, and we're applying the subtraction operator once. So it's a total of 3 operations. Which one do you do first? That would be the next question, right? So what we want to do is understand what this statement is telling the computer to do. And the computer isn't going to do 2 things at once. It's going to do one thing at a time. There's exceptions there. There's parallel processing, multi-core processors. But in this situation, when we're executing these instructions, you do one thing and then you do the next thing. So you have to understand, what is the next thing to do? This operator, and this operator. Now, this operator says, take the thing that's on the right and send it into the output stream that's identified on the left. That's the output stream. So that's called standard out. It's the standard output stream. In our situation, in our case, it's the console window. So this says print something to the console window. This says whatever's on the right-hand side of this output operator, evaluate it, whatever it equals, and then display it on the console window. You can think of it like that. Let's take the characters. There's going to be something on the right-hand side that can be converted to characters, which are then sent into the output stream. That's maybe more precise. So do you get that operator? That's an output operator. It says take something that's on the right-hand side and display it. The thing is, what's on the right-hand side? Is this the right-hand side? Well, look at this. Maybe I'll do it here. What happens if we did like that? 2 plus 3 times 4. Those are 2 operators. Which operator do we do first? We do the multiplication first. So we know this concept of precedence. We have to, we don't always do the operator that's on the left side first, right? That's called, left to right evaluation. So most of the time we do the default order is left to right evaluation. But some operators have higher precedence. Now this operator here has higher precedence than this. This is like the multiplication. And this is like the addition. So we want to evaluate, apply that operator first. That means we evaluate this part of the statement first. We take I and we subtract 6. So what does that evaluate to? 0. If we think that we just entered the loop, this will be 0 because I is set to 6. So what I have highlighted, replace that with a 0. What do we do next? Well, we send the 0 to the terminal window. We evaluate this. Now, this, the fact that 0 is printed at the terminal window, it's called a side effect. And now this expression has that side effect. It has the 0 gets displayed. And then this thing that I've highlighted here is transformed into something new. It's transformed into what? Anybody know? You mentally replace what I have highlighted here with cout. This evaluates to cout. So the output operator always evaluates to the left-hand side. That's it. That lets you cascade output operations. So this whole expression evaluates to cout, which becomes the left-hand side of the second output operator. And so the second output operator now runs, and we print a space. You get that? Is this too trivial? So, so we get a 0, then we get a space, and then we're done that statement. We did 3 operations. Now we're going to do the next statement. We have 2 operations. We have to multiply, we have to assign. We take what's in I, which is 6, and multiply by 6, which is, I is 6, right? So 6 times 6 is 36. So 36 is assigned to I. So I is now 36. 36 is less than 66, so the loop condition is true. That means we're going to repeat the substatements again. In this line here, the first thing we do is evaluate I minus 6. That gives us 36 minus 6. That's 30. This evaluates to 30. We display 30. So we printed 0 and space. Now we print another 30. Then we print 30. So we got 0 space 30. And this evaluates to cout, and we print another space. So it's 0. So what we printed so far is 0 space 30 space. And then we do this statement. And this statement comes in 2 parts. The first thing we do is 6 times I. What's I? I is 36. So 36 times 6, and I'm not going to bother to do the calculation. Let's say 36 times 36 is big, right? So we put something big in I. And I know that 6 times 36 is bigger than 66. So I is a number that's bigger than 66. You can figure out 6 times 36 if you want. But I'm not going to bother because I know it's bigger than 66. And that's all we need to know. Because when I becomes bigger than 66, the loop condition is false, which means we're done executing the second statement of this code. So we printed a 0. Let's look at the answer. We got it, 0 and 30. So that's quiz 1, and you're kind of getting prepared for quiz 1. You're going to practice reading and evaluating code, coming up with the solutions, writing the answer out. So you're learning how to read code. You're also learning how to write code. Here's another example right here. Suppose that t is an integer variable. Write code that prints cold when t is less than or equal to 50 and hot when t is greater than 50. You see the conditional in there? Write code that you should print code when t is less than or equal to 50. So, it's cold if it's less than 50 degrees. And it's hot if it's bigger than 50 degrees. And then you would do this. You would write that, or something equivalent to that. If t is less than or equal to 50, then print cold. Else, print hot. So you're reading and analyzing code, but you're also producing, you're also writing code. So these are actual quiz questions from, past years. And you can use these to kind of prepare yourself to take the next quiz, quiz 1. goes on in there. Okay. But the first task is this command line assignment. And here you want to start practicing, understanding the command line, the terminal window, how to enter in commands here. And I give a list of commands that you should learn. Also, I have this link, how to work remotely. If you have a Windows computer and you don't want to, you could do so many different things. You can install, VirtualBox and run an instance of Linux on your machine if you want. You can install programs that emulate a Unix command line interface and some other options as well. But one simple option is just to log into one of the computers in the lab, which I cannot show you now because the network is down. But I have the instructions here. How to work remotely using SSH. SSH is short for Secure Shell. So secure means the data that you're going to communicate with a remote computer, and all the information that you pass, like your password especially, will be encrypted. So only your computer and the remote end computer will have access to the data that you're sending back and forth. And these are the instructions. And some other stuff. Now, you have to understand what a text editor is. A text editor. What is a text editor? So you need to understand the concept of a text editor. It's a program that's used to manipulate files of character data. So you have these files in the operating system. A files stored on your hard drive or wherever they're stored, and you can display the data that's in those files. Like, let's suppose you have a file that has image data in it, right? So you would open that up into a program that understands the file format. It understands image data. It can render the image to you. If you look at a file that has image data, it's just numbers. It's just a sequence of byte values. But those things, they mean something. They mean color values on a display. And so you have a program that understands how to manipulate the display to represent the color values that are recorded in that image file. So that's, there's a way to render to the user, the intent of the data in the file. And like that, you've got different file types. You've got audio data, you've got image data, and then you have character data. So source code is stored in character data files. It's pure character data. I don't know any programming environments that store machine instructions in other than pure character data format. That means, it's not like, say, a word processing document file, like a Word document, say a Microsoft Word document file. That is not stored as character data. It has character data in it, but it's not pure character data. If you look at it's a proprietary file format that has numeric values in there mixed in with character data values. But source code is not like word processing files. Source code is in something called a pure character data format. So each byte or pair of bytes, it's complicated because of different character sets. But these character data files are simply sequences of numbers that represent characters in some language. and in some character set, not in some language, in some character set. You know, in the old days, when computers were first invented and used, they used a small set of possible character values, only represented the English language. As it could represent all the characters you needed with 8 bits. So you have sequences of, 8-bit values that represent sequences of characters. But, as computers became more universal and applied and used in other language contexts, it turns out that 8 bits aren't enough. To represent, say, Chinese characters, for instance, is what something like 10,000 Chinese characters. So 8 bits isn't good enough. You only get 256 distinct values in 8 bits. So you need more bits. And then so you have to come up with alternative character representations. Those are called character sets. We're not going to get into it in this class, other than what I just said. So it's really messy and complicated. But the character data, and I'm running out of time. I know I don't want to scare you to think that every lecture is going to be this boring. Maybe they will be this boring, but you'll be more active. I'm just talking today. The course is all about you solving problems and learning how to program. And I'm going to be doing a lot of demonstration on how to solve problems. And the focus is for you to do the work. So anyway, that's enough for today. I'll see those in lab who are going to lab.